Hello, everyone. Have you had a good time so far? Second semester, ready for football games? Everybody excited? All right. Okay, so I'm gonna start this class, the first half of the class at least, going through what I need from you and how you can learn a lot through this class by reaching out to your TAs, reaching out to me. So I'm going to give you all the information on what you need to do to ace this class, right? And then we're going to get a short break and come back because this is a long class and come back with the first lecture almost. Okay. All right. So before we start, I want to gauge like what you guys think are some of the most attributes, most important attributes when selecting a product. So let's say you want to go buy a new cell phone, or imagine you are out of college, you got a job as a fresh reliability engineer or any other job that you like, and then now you're in charge of buying something for a production line or for a plant or for an office. You want to order a printer. Okay, so what are the criteria that you may look for in a product? I'm sure you shop. Okay, cost, perfect. All right, got it. Lifetime. Okay. Can you expand? What do you mean by service lifetime? Okay, how long? So I'm gonna write how long it lasts. Perfect. All right. What else? I saw a hand go up back there. No? Shut up. Go ahead. Performance. Okay, that makes sense. All right. What else? Maybe how it looks, what brand it is, um, whether it has warranty, right? Operating conditions. Okay, so what are the specifications that you're looking for? Perfect. So they're all very important. I want to know how you rank them though. So go to this link and rank them for me. And I'm gonna pull up and like get a poll of get a survey of the class. What everybody thinks. I've listed some of these factors that you guys listed here, about nine or 10 criteria. And the survey has 4 parts. Question 1 is ask, I want to know which grade you're at. Are you like sophomore, junior, senior, or graduate? Then I want to know whether you have taken maintainability or not as part of this. That's another class as part of this minor. And then 2 questions about this ranking. One is if you want to buy a product for yourself, what are the criteria that are most important to you? And the other one is if you're part of the company, if you're like that's your job and you're buying a product, what is the most important criteria? Or like you can rank. I will review and get 60. Get them in, get them in. All right, perfect. Let's look at it. Okay, so this is mine. All right, so most of you haven't taken that class. I'm going to speak a little bit about maintainability today, but that's obviously the focus of the next class in minor that you're going to take. Okay, let's look at our ranking. It seems like performance is the top, then maybe cost, then look what came third, last a long time, then maybe service, appearance, easy to repair, okay, warranty, and so on. And this is when you're buying for yourself. Let's see what came up when you're buying for. Can I order these somehow? So performance was the most important when you're buying for a product line. And then last a long time, that came up second. And then cost, easy to repair, that came up fourth. Okay, so I'm glad to see that because you know what last a long time means, right? That is this class. You want things to last a long time. That is reliability. So you are in the right class. And then easy to repair. What is that? That's maintainability, right? So that's the next class. That's why these are important. Okay, so we are thinking very close to general public. There was a Gallup survey going over this ranking, and they got performance as a top factor. That's a long time. Came up as the second most important, which is essentially reliability. And then the fourth important was easy to repair, which is maintainability. So, okay, so we know that this is all important. Okay, so if we know reliability is important, let's define it. What is reliability? Lasts a long time, right? It has a time component. All right. What else? It wants to maintain a performance for a long time, right? So performance or function. What's the next component? When we talk about reliability, okay, traditionally, like a traditional view to reliability, making sure that things last for a long time, was to over-design, right? You want a bridge that allows a truck to pass, right? Maybe design it for 10 trucks, for it to have the capacity to allow for like 10 trucks, and then maybe you get it right for one truck, right? So over-design. But the problem with over-design is that it's very expensive. Like it takes up a lot of resources. We want to do things much better, right? So that's why we need to come to this to this reality that everything almost is probabilistic. Let's think about probability, and let me put it down because that's something that we're going to spend almost half of the class on. So okay, so think about life in general, right? Almost nothing is deterministic. Right, if I have a coin and I toss it, right? I give this example in my probability class. If I toss it, if I know the number of molecules in the air, if I know the temperature, if I know the humidity, if I know the right angle, the force, everything, I may be able to simulate the process and get it right, whether it's gonna land on a head or a tail, right? 100% of the time. But is it worth it to deal with that much complexity? And if so, can I really model a system that exactly to capture everything about this? Or is it better that I deal with it in a probabilistic manner? Say that, okay, I have a fair coin, half and half, like I get a tail or I get a head. And then try to use that to take advantage of it. Okay, what's the likelihood that I'm going to have like 10 heads in a row, right? To be able to describe my system in a probabilistic manner instead of modeling it as a sophisticated deterministic manner. And sometimes that may not even be possible for a lot of components that we deal with on a daily basis, right? We may not even be able to characterize their physics, the underlying physics behind them in a deterministic manner. So we need probabilistic approach, statistical approach to deal with how long things are going to last. Okay, so what's the last important thing when we are talking about reliability? We want a certain performance for a certain amount of time, right? And we want to deal with it in a probabilistic manner. What is the probability that this component, this piece of equipment, lasts for X amount of time and maintains its performance level? Right? What is the missing piece? What's the last thing that's important? Let's think of my cell phone. I don't have one of those fancy samples. So this is just a random cell phone I bought from the brand, right? Okay. So if and my cell phone is not waterproof. If I drop it in the ocean, is it the cell phone problem or is it my problem? Can I say that my cell phone wasn't reliable, or is it that I used it in conditions under which it wasn't allowed to? Right? So operating conditions is the last missing piece. So these are the four most important components in reliability when you think about reliability. And this is essentially the definition of reliability. Okay, so let's have an example now. Let's say, again, you graduated, you're on the job, you can either go to, like, I don't know, manufacturing, or let's say chemical engineering. If you're a chemical engineer, you may go to a plant, a chemical plant, or I don't know, work at any job. As a reliability engineer, you're wearing this hat that you can, essentially, you've taken this minor, you can act as a reliability engineer. Yes, let's say the company puts you in charge of an asset, right? Here, our asset is a 1972 Ford pickup truck, right? It's an asset. It has multiple parts into it. It has a motor. It has a controlling, control, a place where you can control the machinery. Then you can operate it. Let's say you want to use this pickup truck to move some kind of material from point A to point B. Right? So there are 5 pieces into this pickup truck, for instance. Let's think of them: headlights, air conditioner, brakes and tires, and seat belts. Right? Five of them we want to focus on. Now I have a question for you. I want you to show me, by the raise of hands, which of these components you think is the most critical aspect of this asset or this piece of equipment. Who thinks the headlights are the most important? Good question. Okay. So let's continue with the current assumptions that we want, and let's assume that we want to use it for moving some items or like something from point A to point B. Right? So it's just move, like essentially hauling stuff from point A to point B. Is there any other question you want to ask me? That is a very good question. Okay, that's a very good question. Okay, so let's go through the ranking and then move on, because that is exactly what I want to get to. Operating condition. Headlights. Who thinks headlights are important? Maybe not if you're not driving in dark, right? Okay, before giving you all of these other pieces of information, which one would you have said that are the most important or the most important part of the asset? Okay, brakes. Okay, exactly. That's all right. Safety first, right? Brakes. But I can give you another piece of information that you should have asked for immediately after I told you we have an asset. How do you want to operate this asset? What are the conditions under which this asset runs? If I'm using my truck to only during only daylight hours, I'm only driving at 50 miles per hour, and my facility is located in a desert, then you will change your ranking, right? You may think that now the person who is driving this car is more important. Maybe we need a air conditioner. Brakes, maybe not as important. Driving 15 miles per hour. Headlights, not at all, right? So you have to know your operating conditions before you can even start thinking about reliability. Okay, so hopefully these at least get you motivated thinking about reliability. And with that, I want to just introduce myself and tell you more about what you can expect from the course, and then move on to introduce your TAs, and then take your questions. Okay, so I see a lot of familiar faces. So a lot of you know me, right? Okay, I'm Anahita Kojandi. I'm with the Department of Industrial and Systems Engineering. This is my 5th year here at UT. I graduated from University of Pittsburgh, so I was very happy to move south to not need like 15 layers of code when like during January, February. I'm originally from Iran, and this is the picture that most people envision when they think of Iran. But and some part of it is actually like that. But we have a lot of other places in Iran, and actually the last picture, it always reminds me of Lake Tahoe for some reason. So we have a lot of different scenery. And again, when you think of Iran or Middle East in general, you think ancient. Yes, we do have a lot of ancient stuff, but we do also have a lot of new stuff. This is the city I came from. It snowed there, so there you have it. All right. So about my research, I want to highlight 3 projects that I'm currently working on very quickly, and I'm not highlighting the one that are more closely related to reliability because we're going to talk about reliability during the entire class. So I wanted to show you that you can have different interests, and actually I'm bringing 3 examples from 3 different topics or domains. So the first one is about placement problems, particularly when we are placing green infrastructure across a city, across a watershed. And so this is a very familiar piece of news these days. So we get a lot of flooding, a lot of rain these days, and we have a lot of hurricanes, and the infrastructure is not prepared because when they design infrastructure, right, for mitigating flooding, for like directing this water to maybe rivers or something, they designed it based on the historic information, and a lot of things are changing, and a lot of construction is happening too. So we are adding to the impervious area in our cities, which when you have like rainfall on impervious area, they don't get absorbed by the soil. They just turn out to runoff, right? And then we get flooding. So there are ways that we can mitigate that right now. So for instance, we can use green infrastructure, including bioretention, rain gardens, and so on, to mitigate flooding slightly in the city. So here is another example. Yeah. So these are called porous pavements. So they are so they don't allow the water, at least, so they are not like impervious areas that you see, like they are not like your regular pavements. They don't let the water run, and then they help with like slowing down the runoff process. So okay, so let's say we have all of these nice infrastructure now, green infrastructure, porous pavements, and so on. Where should you place them in your city? Based on the criteria of the land, based on maybe the slope of the land, maybe based on the cost, based on where do you have most impervious area, where do most expensive buildings are located, right? So you can ask a lot of these questions to come up with criteria on where to place all of these pieces of green infrastructure. What complicates a lot of these placement problems is that we don't have one projection of how things are going to go. We don't have one projection of how much rain we are going to have. There are a lot of institutes around the world who are trying to predict when it's going to rain, how much, at what intensity, right? But they don't always agree. Their models are all based on very solid mathematical, physical formula, right? But they don't always agree in terms of what kind of projection we are going to have. So consolidating all of these projections into an actionable plan for placing all of these green infrastructure is one of the tasks that we are doing right now as part of our research project. The next project I want to highlight is a completely different domain. It's in intelligent transportation systems. So you're all hearing about autonomous vehicles and how they're going to take over, right? But we are obviously not there yet. We don't have systems that can operate under every condition. We all are familiar with human drivers. and the crashes. Maybe some of us have been involved in crashes before. And then automated driving, for instance, Teslas, or I don't know, Ford is doing a lot of research, Audi is doing a lot of research. They have this promise that, or Uber, that they're going to have automated vehicles on the roads within the next few years. But every now and then we hear about another crash. The color scheme was wrong. It was foggy. It was too late. It was too dark. Right? There are conditions under which these systems cannot operate, at least with the current algorithms, with the current sensor system that we have. So, okay, so in the future, maybe in 20 years, 30 years, we can accomplish this fully automated intelligent transportation system. But meanwhile, during this transition period, what should we do? What if we have smart vehicles who can understand their limitations? They know that, oh, this situation, I'm getting bright light. It's too dark. I cannot handle this situation. I have to alert a human driver to safely take over the control. And then switch back and forth between the human driver and the automated system to be able to navigate from point A to point B safely. So we are developing algorithms that allow the automated vehicle to switch essentially the driving entity. And here is, for instance, a chart. I don't know how descriptive it is. I just got it from one of my previous slides. But then the thing is, we have different environment that's dynamically changing from low risk to high risk and all the way back to low risk again, right? And then in this example, we have manipulated the risk on link 4 to be exceptionally high for the automated vehicle. So we see that we start with an automated vehicle, we switch the human driver, we start with a human driver, we switch the automated vehicle because it's safer for the most part. And then on link 4, we have manipulated the risk of automated vehicle to be super high. So it switches the entity to be the human. And then after that, it switches back. So that's the change of the colors. So essentially, our algorithm is capable to understand that the risk is increasing, and as a result of that, it should switch the entity in charge to and back to and from the human driver. All right. Last part, the last work that I want to highlight is in data analytics and predictive modeling with applications in healthcare. Who has heard of sepsis? Nobody? Few people. Okay, sepsis is one of those problems that most people haven't heard about, but it kills a lot of people, unfortunately. And it happens mostly in the hospital setting. When you have infection and your body is weak and responds to, and it essentially responds to infection in form of inflammation, your body starts to deteriorate very fast. And out of people who acquire sepsis, which happens typically at a hospital setting, 50% don't recover. And if it progresses and it goes undetected, the rate goes higher to like 70% and 80% and so on. So the risk of the chance of recovery decreases in time. So acting in time, early prediction is very important. So that's why, and here is essentially a timeline of the disease or the complication. So you have the time for recognition, right? That happens at the bedside, and if the intervention is not effective enough, it may end up in death. There are systems there are algorithms for detecting sepsis at the bedside right now, but they are typically rule-based, meaning that they say, oh, if your heart rate is greater than something and blood pressure is greater than something and your temperature is maybe lower than something, then you have sepsis. But these rule-based algorithms miss important things about from that change from one patient to another patient to another patient, right? So we are trying to build algorithms that are adaptive and that respond to individuals. Okay, so what we are doing is we are using a window-based approach to analyze, and then using machine learning. So we are using machine learning to learn from historic patients who have acquired sepsis to see who this new person is similar to, and then given that, what is the probability that given these physiological information about the patient, they are gonna acquire sepsis, or and that way we are predicting sepsis. So we are using this window in time and generating a probability for each patient at the bedside. So here, for instance, our probability starts from very low, and then at around 100 minutes, 90 minutes before time of sepsis, as it would have been detected by rule-based algorithms in our early warning system, we predict that this patient is going to have sepsis. So this allows at least an hour and a half earlier for bedside staff to come and take care of the patient. And of course, an hour and a half may not be enough to act. So we are working on other algorithms which are enabling us to predict 6 hours earlier, 4 hours earlier, and so on. So it's kind of like reliability. You want to predict when things are going to go wrong, but we are using non-parametric approaches, machine learning approach for that prediction. All right. So with that, at least you now know at least a little bit about what I do. But I want to talk about the class a little bit more. Okay. So this class, in this class, we're going to talk about why we study reliability and go through design for reliability. Maybe I should call it next class because it's going to be after the break that I'm going to give you. Next class, we are going to start talking about R programming and data. Again, some of you have taken priority class with me, so you're hopefully proficient with R. But if you're not, or if you haven't taken the class with me, I'm going to go over everything again. So I'm going to introduce R. I'm going to tell you where you download it here today. And then we're going to get started in class with R. So throughout the class, I'm going to show you the math. I'm going to show you formula, and I'm going to show you R. In exam, in your homework, you're allowed to use either one. I don't want to require you to use one, but I highly, highly recommend that you start learning R and using R because it's going to be much more it will save you a lot of time during exam. So you may need to write a lot of things to figure out what is the time to failure if you're doing the math or if you're doing the formula. But essentially in maybe a line of command, you can get that number in R. So I recommend that you practice with it and get comfortable with it. You are allowed to bring your laptops to exam. So you can essentially be done with the exam in half the time. I'm writing the exam, I'm giving you time to be able to do it by hand. But then if you're doing it in R, you're gonna get it done honestly in half the amount that's needed. So I totally recommend that you invest the time, and as we move along and I introduce all of the the equivalent of math as well as the R command, go with the R command. Okay. So we are going to do I don't want to say quick, but we are going to skip over some concepts, but we are going to do a review of priority. So again, if you have taken priority with me, I'm using more or less the same slides, so you're ahead. But then for those of you who haven't taken priority with me, again, you may or may not be familiar with all of these concepts. Some of you have waived priority which was a prerequisite for this class. I recommend that you show up to those classes and study with us when I go through priority. I review it for a couple of sessions. So the next couple of sessions, the next couple of weeks, we're going to spend time reviewing priority because that is the backbone of reliability. So I want to make sure that everybody is up to speed with their priority knowledge. Okay, so we're going to talk about some of these concepts you've seen before: PDF, CDF. Some you may not have. Reliability function, hazard function. We didn't cover them in the priority classes because they are specifically related to reliability. So we are going to cover them here. We're going to talk about censoring a little bit. We're going to talk about bathtub care, which is one of the important reliability hazard functions related to reliability. We're going to do life distribution. So again, you're familiar with some of these distributions. I bet you're familiar with normal distribution, right? Okay. You're probably familiar with exponential, right? But not so much maybe with log normal or Weibull. Weibull is a very important distribution when it comes to reliability because it's very flexible in terms of the behavior it can present. As a result, there is a component in this class that's called life data analysis, right? And it is equivalently called Weibull analysis. That's how important Weibull is. As a reliability engineer, you should always know how to do Weibull analysis, and we're going to cover that in the first half of the class. Then we are going to move on to reliability diagrams. After understanding what a certain component, what are the reliability specifications of a certain component, we want to know how to build systems from these components, right? We want to know how the reliability of the system would be if I put together, for instance, two components in this format compared to this format. Which one is going to have a higher reliability and why, right? We're going to go through complex systems and then build all of these blocks together and build giant systems that you're going to analyze later in the class. We're going to have speakers in this class talking about root cause analysis, which is an important aspect of your job if you start as a reliability engineer. Understanding why something went wrong and how you can use that to learn how to avoid it next time. We're going to talk about FMEA, FMICA, to understand how you can prevent things from happening, failures from happening. Then we're going to go to state-dependent systems. So if you have two, for instance, motors, if they're connected to each other, but they don't interact with each other, how is that different from the fact that you have two motors or two components that are interacting with each other? Let's say if one fails, the load on the other one increases. We're gonna analyze these interactions, which are gonna make the model much more complicated. And at the end of the class, if we get time, we're gonna go to reliability allocation and reliability testing. But we touch on all of these concepts throughout the class. All right, so here is the big picture of what we are going to cover in this class and when. Obviously, things may get shifted depending on how fast or slow we're going to go. And we are going to have a few speakers in this class. So I am responsible for teaching you the math, the computer coding background of it, right? I'm going to bring speakers who have practiced reliability for years and years, for 10, 20 years. And you can ask them a lot of questions. In the past few years that we have offered this class, that is one of the favorite components of this class for students, because they get to interact with people who can potentially be their bosses. And throughout these interactions, some people actually got internships or got job offers. So I recommend that you show up for these guest speakers, for our guest speakers, and be attentive and ask a lot of questions. Okay, this is our textbook. I post all of my slides online. You can use textbook to make sure that if you missed something in class or you need more in-depth information about it, you can refer to the textbook. So R programming. Who is familiar with R? Who has R already installed? Okay, most of you. Perfect. If you haven't, don't worry at all. We're going to cover as if it is not a requirement for this class, so I'm going to cover it from scratch. So I want you to download two packages. You first go to this link and download the R package, R software. And here is like a mini instruction on how to do it. And then part two, I want you to install R Studio, because this has a nicer interface. This gives you a nicer GUI so that we can, once you plot something, you can see it at the same, like on the right-hand side, like easily available. And you have nice controls over some functionalities. Okay, so two links, two packages. You have, don't forget about the second one. And you can get started right away by writing basic programs. But then again, we are gonna, the statistical stuff, we're gonna cover in class. Question? Yes, actually they already are. So they're already on a Canvas. And I try to post them ahead of the class because some people like to annotate. So if you're one of those people who like to annotate on the slides, and there are going to be a lot of examples. Today is going to be mostly lecture introduction and like mostly high level stuff, but we're going to get into the math next class. So if you want to annotate, feel free. And again, feel free to bring your laptops with you into class. I don't mind. All right, breakdown of grading. You're going to have homeworks every week. We're going to have quizzes every week, 2 exams, a midterm exam and a final exam. Exams carry a lot of weight. So make sure you prepare yourself for the exams. Okay, so and then I don't take attendance. I understand this is late. You may have other other places to be, or you may be too exhausted at 5 p.m. that you don't want to come to class, or your brain doesn't work at that time. So I'm completely fine. So you can watch the videos through streaming live, or you can watch it later when we post them on YouTube. We have a youth class YouTube channel, so you can watch it later, right? But I encourage you to come to class if you think that especially if you're falling behind, or if you think that the interaction helps you. And like one thing I do in class is when I give you work examples, I try to do, it's not quite flipped classroom, but I walk up to you and like you can ask me questions and I help you, guide you through like how to get started with stuff. So I think there is a lot of value, and our RTAs are going to come to class as well, and they're going to help you get started. So I think it's a good idea to come to class. But again, it's up to you. I'm not taking attendance. One thing that I'm taking attendance for, and I give you bonus for, is for guest speakers. I want you to show up to guest speaker classes and ask questions and be attentive, because I want them to see how much you value the time that you're spending coming here after work and essentially giving lecture to the future generation of reliability engineers. So that, and for that, I'm gonna reward you. So up to 5% you can get for attending all guest lectures. And I announced before that, so you have this in your in the syllabus, and you have it here in your slides. So you know when guest speakers are gonna be here. Typically, our guest speakers are gonna start speaking the second half of the class. So I teach for the first half, and the second half guest speakers are gonna come. So if you want to skip my class and come to guest speakers, you're welcome. I'm not gonna hold that against you. Again, I don't take attendance, but I want you to show up for guest speaker lectures. Okay, and all assignments and quizzes must be submitted through Canvas, so no paper, because we want to make sure that we are doing good housekeeping of everything. And if you have any issues with grading, everything is in the system. So everything goes through Canvas. Everybody has access to Canvas. We checked. Okay, good. If you don't have access, work with OIT and get access to Canvas if for some reason you don't have access. All right, homework structure. Every week you're gonna get a homework. There are two parts. There are two links for your homework. First part, it's a 2 to 3 question, 8 points. The homework gets posted Friday afternoon, early in the afternoon. You have almost a week to work on homework, and then you have to submit it before class. There is no extension, no nothing. Our class starts at 5:05. I want to make sure you put in your homework at 5. And no extensions. If there is something, you have to miss it. If you're going to a conference, presenting something, you're not going to be around to submit homework or something, work with your TAs ahead of time. Email them, let them know. And they can go to the system, manually extend the deadline for you. Right? So no going back to them and saying that I missed the deadline, I want that extension. Be proactive, engage them. Okay, so this is basic homework. You all have turned million homeworks. I have no doubt you have no problem with it. Okay, in this class we have a twist. You said, remember I said there are two parts into your homework. There is an 8-point homework assignment, and then there's a 2-point submit your own question. Okay, what is that? So every week, based on the material that we cover in class, you get to submit your own question. Think of stuff that I haven't asked you, or think of stuff that you find interesting, right? Or like go to the internet, go to the book, find a question that I think is challenging. Find a question, post it along with its solution, because I want you to work through the solution yourself. Okay, and then you get automatically 2 points for that out of 10 points. So that's already a bonus. Okay. But then what happens is that before midterm exam and before final exam, we go through the questions that you posted. If you like your question, I'm going to choose it and I'm going to put it in the exam. So and then feel free to bring your solution with you if you're confident that I'm going to pick your question, because then I don't mind. You can just write the solution. You have it. This is what you earn for writing good questions. So write good questions. They may end up in the exam, and I guarantee I'm going to use at least one question of what you're writing in the exam. And if the questions are good, I'm going to use 2. So write good questions, but again, one time it happened that somebody wrote a very good question, their solution was wrong. They missed it. They missed the opportunity to get it right one more. So make sure your solution is right. Because to me, that's another part of learning. I want you to critically think about something and come up with an answer. Then we have quiz. Quizzes are going to be posted every week on Tuesdays. Our class meets on Thursday, so you have almost 48 hours to work through quizzes. They are 10 points, typically 5 questions, and you get 2 attempts. So your questions may be different. There's a pool of questions that at every attempt you get 5 questions. It will show you your total score. It won't show you which one you got right or which one you got wrong. But if you choose to, you can attempt a second to give you the best of the 2. So if you are not happy with your grade, just go for it another time, and we'll get the best of the 2. No, they're not time. All right. Okay. So there may be problems with grading. Again, with quizzes, sometimes they act out, they don't give you the best of the two. There are glitches in the system. Or there may be issues with grading, anything. You have to, or like with exams and everything. For every complaint or every request that you have, 2 weeks. This is a large class, so we have to keep it very organized. So we try to give you feedback within a week time frame. You give us feedback within 2 weeks time frame. If you're unhappy with something, see us about it, great. 2 weeks, that's it. So come see us. I'm going to use the default schema for grading. You have it for your reference here. Here we don't have A+, so A+ is A, but the rest is that. Okay. And this is, by the way, this is for undergraduates, I think. I don't think graduates have all of these levels. They are all collapsed, or some of them are collapsed. So be careful about that. So I don't think like, I think graduate doesn't have B+, or like some of these levels are collapsed. So they're gonna be collapsed. Just be careful about that. All right. Seeking help. So I told you what I want from you, right? To be able to ace this class. So you can always seek help. You're not alone. Come to class, and again, you gotta get one-on-one time feedback from me and from the TAs. We are gonna have office hours, 2 office hours, 1 on campus, 1 online, 2 chances. And again, they are on Wednesday and on Tuesday. Your homework is due on Thursday, so we strategically set them closer to your deadline in case you have any questions about your homework, about quizzes. Again, we cannot give you the answers, but we can guide you. So make sure you reach out and seek help. Here is the information for on campus. For online, you can interact with your TAs through Zoom. And obviously, an ad hoc manner, you can have by appointment to seek help, by appointment like meetings. And here's the class email. Please only direct your emails to this email address. If the TAs see that they cannot answer you, they will forward your email to me. So don't directly email me, because I'm using my email for my research, for a lot of interactions. I get 100 emails a day. I don't want to miss your emails in between my other emails. I want you to get quick response to your email. This account will be checked twice a day. One time in the morning, one time in the afternoon. So you can have a good estimate. Like you can expect a response within 24 hours. And be considerate. If you are asking a long question, go to office hours. So don't email math or formula in an email. Just be considerate. Again, think of the size of the class. We have almost 140 plus students in this class. 100 in class and another 40 on offline, or like online rather. So it's a large class, and be considerate of our nice TAs. Speaking of our TAs, I'll let them introduce themselves.
So hi everyone. Because everybody likes to know my hobby, video games, working out and food. We go to the next. But yeah. So for my research mainly is working. My research is mainly focused on solar panels, which we call them photovoltaic panels. Like combining them with green roofs, which are roof gardens, or working on them when you're combining them with lithium-ion batteries, because they are becoming the trend right now. So to invest on them. At the same time, I work on supply chains. I mainly do mathematical programming, but I've done simulation as well. Or this summer, I went on an internship at Monsanto, if you heard of the company. I hope you heard good news on it. So yeah, I've been there. I started to do a lot of simulations there. So that's me.
Hi everyone, my name is Najmuddin Akundov. I'm from Azerbaijan. Just in case you don't know where is the country, I just show it on the Google Maps. It's between Caspian Sea and Black Sea, which is called Caucasus region. My hobbies are studying games and swimming, and hopefully we have two Olympic-sized swimming pool in UT campus. So I'm very happy with that. Okay. I did my bachelor in my home country, Azerbaijan, in industrial engineering, and I did my master in Canada, University of Waterloo. Then, actually, I started my PhD at NJIT, New Jersey Institute of Technology. After 1 year, I transferred to here at UT. And my current advisor is Professor James Ostrowski, and I'm working on power systems, student commitment problem, and vehicle routing problems. And this is short development. If you have any questions about the class, you're more than welcome to come to PARs.
Good afternoon, everyone. I'm Omid Purkalili. I'm coming from same country as Dr. Khojandi is coming. And my hobby is walking, driving the pet. I'm tired. Chess player. I put reference for you that shows the daily average walking not bad. 3.4 miles. And yeah. I did my bachelor in mechanical engineering. Then I continued in industrial and systems engineering. I moved to US in 2016. I worked for a company in Columbus, Ohio, and then I got admission here at UT for PhD in industrial engineering. My research focused on supply chain management and lean production. My advisor is Dr. Sani. Some of you are familiar with him. We are working in some project right now. I saw one of kind of my, I would like to say colleagues. We work in a boat-made company in a project related to lean production. And yeah, we are here to help you in any way we can. We are here to help and support you for all assignments and everything. So feel free to email us and meet us in office hours or send us email. Yeah, we would be happy to help you in any way. Thank you.
Perfect. So now you know you have the faces of your TAs. So when you email them, you at least have an image of like you're interacting with folks who essentially went through the same program as you are going through. All right. So for distance students, you can. A lot of you are like watching right now live through Zoom, and later we post this video on YouTube. Okay, I saw one of distance students ask a very cool question that how attendance is going to work for them. So don't worry, if you are in the distance section, we're going to hold you to distance. So you can join through Zoom. We're going to get an attendance through a snapshot through Zoom. And if your name appears as a list of attendees, you're going to get credit for that. So that's how we are going to take attendance. But that only works for distance students. If you're on campus section, I bring a physical signing sheet during guest lectures, and then you need to sign it. For distance, you don't have to come to campus. I understand some of you are working, some of you are even in other states, so don't worry about it. Your attendance counts as your online attendance. Again, I want to show that we care about our guest speakers and care about their time. Okay, for your exams though, regardless of whether you're distance on campus, on campus, you have to come to campus to take the exams. But for distance students, I understand some distance students are actually on-campus students who, because of the capacity of the class, took the class through the distance section. I strongly prefer that you come to campus to take the exam. I have reserved extra rooms, so we have room to seat everyone. So come to campus, take the exam with us. It's better because if there is a problem with a question, and sometimes it happens, I comment on that during the exam, and then you are aware of it. So, and you can ask questions. So it's better to take the exam on campus. Please come to campus. If you are in the distance section, and if you cannot come to campus, then you can take your exam using a proctor. I have already posted the instructions for who can serve as a proctor, what kind of email you want us to, I want you to send us, and everything. just know that for the midterm and final, I want you to send me 2 separate emails. For the midterm, send us the email by Monday, 9/24, September 24, and let us know the information asked and detailed on the Canvas assignment announcement, and send it to this email address. All right. Okay, now I open the floor. Any questions? Anything that I missed to mention or I haven't covered? Oh, about exam, maybe. Exam is going to be open note, open books, open laptop, no internet. So again, when you're doing your homework assignment quizzes, use R, and then be prepared to use it during exam, because it will cut the time you need for exam by half. No questions? No question. Okay, one question. Go ahead. No. You can watch them live online. The only thing that I care about is attending guest speakers. For that, if you, and again, you may choose not to. I don't think you. The thing is, you don't get the bonus. So I'm gonna, like, for instance, I don't know, I think we have 6 guest speakers. So every one that you show up to, you get 5/6 of a point, because I give you up to 5 point extra. So if you attend all guest speaker lectures, you get up to 5 points extra, which can essentially shift a letter grade. So that is a good way of kind of making up for things that you possibly may have missed. But if you don't need it, or if you don't want it, or if you can't, again, I'm not going to hold it against you. Feel free to not show up. Question? Yes, but then I call the textbook required. So I want you to go through it and read the textbook from a different perspective, because I'm presenting you from my perspective. Textbook is presenting you from different perspectives. So all of them are complementary. But anything that I ask you in exams and quizzes and homework, I cover in my class. But again, you can think of it as a required textbook. Anything else? No? All right. So let's take, I don't know, 10 minutes break and come back. And then we start our next class. Email me. There was one other student, and also email OIT. See if there's a problem with the course or whether there's a problem with the doesn't show up. Because I added it like Sunday. So it was really interesting. Okay. So yeah, but if you can also follow up with me and OIT, don't worry about the time. Send it to me. And also follow up with OIT. Let's figure out what it is, because here's the same thing from another student. But now I'm thinking maybe it's something that everybody is. Because I know it said I signed up for just like a 10-seat class. So I wonder if Maybe because it didn't show up. I merged all of the sections that I had, and the material science wasn't part of it. I started having industrial, nuclear, I think, and I used in material science, but strangely, when I was
same issue.
yeah. So check it out, I think also like you and then you can also get there and like get there.
Thank you.
Just do it quickly because I'm gonna post for work tomorrow. Canvas. Yeah.
Thank you.
I haven't checked the older version, but I would think that these concepts don't change. Like, it's not like the, I mean, they're very solid mathematical background, so I don't expect a lot of difference between the older version and the current. If that's easier for you to get it, I think it should be fine.
I don't know why this is like this, but all of my classes are saying that it's not public. I want to go down there.
So your material science, I had a conversation with somebody else. I don't think material science is assigned to me. For some reason, I'm missing material science section completely from
So
my
there's
calendar.
probably something going on with the office.
Yeah, if you can email OIT and like get them listed under, because when I log in, I don't see material science. So, but then what yeah, you have to talk to somebody who does this. Yeah. Yes.
Okay, is it going to be split in like lecture and then guest lecture?
Yes. Okay. So those lectures are gonna like, or like those sessions where we have guest lectures and teach for the most part up to start. We get like 10 minutes a day. Most guest lectures start at 30. But like sometimes they start earlier, sometimes later. So depending on like, and I try to like let everybody know. I try to email you. But like assume that everybody starts at 6:30 unless I mention. Okay.
Okay, thank you.
Oh, by the way, why is this so hard?
I mean, it's the first one. So we should not post it early.
Yeah.
We'll just
Okay. How's it going?
I was wondering, do you think we'll use the full time every class? So like 7:45 each?
If I see everybody's tired, I probably will be though. But then, I mean, the class is late, so
Yeah.
not a whole lot I can do about it.
Okay, I was just wondering, like,
Yeah, today probably like I'll let you go about 7. But yeah, for a couple sessions, yeah, we have to sit because I want to make sure that I get priority covered.
yeah, I'm just scheduling like when I should bring dinner. I'm gonna have from like.
Oh, you
noon.
can bring dinner to your class. I don't mind. And like a lot of people do actually, because like it's a late class. It's a 3-hour late class. So bring something to eat. I don't know. No chatting though, but like you, yeah.
Okay,
Fine.
thank you.
Yeah. Yeah. I think that's a better idea. I agree. All right, it seems that everybody's back. Let's start. And if I get through what I want to cover today, I'll let you go early. Yeah, exactly. And that's the other thing, that this class is kind of late. So I try to not be very strict with things. If you want to bring your dinner to class, I'm totally fine with it. Yeah, so I totally understand that this is like a large class to begin with, and then it's like late. It's 3 hours. You're already exhausted, and then some people like football and they're missing it. So NFL, I don't know. I understand all of these. So I want you to, if you show up to class, put the work, do the exercises, and be with class. If you don't want to show up to class, again, it's completely fine by me. But I think you take the most out of this class if you're actually engaged with it, and it helps from others from sleeping too. So be attentive in the class. All right. So speaking of attentive, let's start with priority and go through the points, and then I have a question for you. Okay, so we define reliability to be the probability that an item will perform an intended function for a specified period of time under stated conditions without failure. And then the 4 points were probability, function, time, operating conditions. And we talked briefly about all of them. We're going to speak more about them throughout the rest of the class. So we have different objectives as reliability engineers. Sometimes we are using our techniques in the design part, right? We want to make sure that the product that we are designing is reliable when it's gonna go to the hands of the customer. Sometimes we are using reliability to avoid failures in a product that's already designed, right? By maybe using a couple of them in parallel, or adding redundancies to the system, or derating, or some of these techniques. So there are two major aspects into reliability engineering objectives. But before that, let's start with why do we care about reliability? Why reliability matters? Why is it important to have a reliability? Safety. Okay, operation. So they can perform, they can be available, availability. What else? Efficiency. Okay. What do you mean by efficiency? Okay, so you want efficiency. But I'm mostly thinking like maybe I didn't clarify what I'm asking. So as a customer, think about the customer, think about the market, think a little bit bigger, not as an engineer. Why should people care about reliability in general? It sucks for something to break as soon as you buy it. Okay, so if you are the customer who bought something and it just broke, how would you react? What would you do? First thing. Okay. So warranty cost. So that's going to cost the company, right? Because they have to replace the part. What else? If you bought it from somewhere, you probably go on vents online, right? That, oh, I bought this product. It sucks. It broke right away. Don't buy it. So it may cause market pressure, right? It may impact the sale of that company, right? So there, okay, we talked also about safety. So what else? Safety can be risk, right? So it can cause maybe damage, or it can to them, to humans, to whatever, right? But what else? What are the bigger aspects of safety? So it can cause liability, right? You can bring lawsuit to the company. So it can, and we are going to talk about all of these. So there are a lot of aspects into why reliability matters. Let's look at an example here. From 1979 to 2010, Ford and Mazda had some kind of strategic partnership. Ford asked Mazda to build transmission for a car it was selling in the US, and they were both supposed to use the same identical components with the same identical sort of specifications. Ford adopted zero defects as its standard. So zero defects means nothing that's faulty can leave the plant. Right? Everything is within specifications. Okay? They produce stuff, they produce these transmissions and let them go, right? And then people started using them as part of the cars. This is the warranty cost. We talked about warranty, right? This is the warranty cost. Ford incurred 5 times almost as much warranty cost as Mazda. Okay, what happened? They both had parts, zero defects. Left the company, left the plant. What happened? What do you think happened? Let's say these are proportions. That's a good point. Maybe these are proportions. Think about the 4 components in reliability. We talked about performance. We talked about operating conditions, right? So performance, this transmission needs to work. Operating condition, they are both in vehicles driving on the road. What else? There is priority and there is time. What is zero defect leaving the plant? In the beginning of the time. At time 0, right? Everything was perfect, no defect. What happened maybe over time? You want to go? Ford had a smaller time to failure, right? Why? Something happened. Something happened that reliability of components were lower, even though their quality was the same, right? And this is what happened. Everything was within lower bound and upper bound in the acceptable range, but they were more on target with Mazda compared to Ford, right? And then these parts over time, the wear and tear of all gears in the gearbox or whatever, like engaging each other, it kind of caused a lot of damage over time because of the tolerance. So this is the one of the differences of quality engineer and reliability. You are designing not just for the fact that you want something to have a high quality, but you want that high quality to last for a long time. So this is the time component that plays a role when you're thinking about reliability compared to quality. All right. So you can think of quality and reliability as being highly correlated for the most part, but they have differences as well as when it comes to time. So quality is when something is manufactured according to certain specific design criteria or tolerances, and reliability when it can maintain that kind of design characteristics for a long time. Okay, let's think about another example. Let's say you have a 2-year-old HVAC system, and it's like 95 degrees, super hot. Then in the middle of the summer, it fades. You have to spend $700 for service of this HVAC system. And then the repair person comes, fixes it, and they mention that, oh, by the way, I just fixed another one last week for this other next door building. How does that make you feel? If you know that this is a well-known problem with this particular piece of equipment and nobody has fixed it. So again, think of the reputation of the firm. Think of the brand. That's one of the things that we all care when you're buying it, right? So that's another thing that affects the brand. It affects. So it can essentially cause a lot of loss for the company in the long run if you don't invest upfront in the reliability of the components. Another factor is competition. So if you have products that are comparable in terms of performance, but one lasts a much longer time and the other one doesn't, which one do you think will have more customers? So US manufacturing lost a lot of market share because this was the rate of defects per 100 cars for a lot of the US manufacturing in around like 1980s, and then 240 per 100 car defect. 240 defects per 100 cars for Japanese manufacturers around the same time. So obviously, a lot of American cars took a hit because of that. And then since then, obviously, things have changed. But you have to be careful about the brand, the reputation, the competition. And that's one of the aspects that pushes reliability to the forefront. So it is all about product value and the value you can bring for your customers. And customer value obviously is the value of the product. The other factor is liability. We talked about it a little bit, and so there has been a lot of cases for litigation or with lawsuits for different pieces of equipment, at least related to vehicles, related to cars. Anybody had to change their airbag because after this whole thing, airbag problem with Takata? A lot of airbags were recalled, right, across the U.S. It was one of the biggest, I think, safety recalls in the U.S. history. And last year, Takata filed Chapter 11, right? They filed for bankruptcy. So it can have a lot of consequences if you don't do proper reliability testing as part of the life cycle of the product. And if you don't design for reliability, if you account for all of these factors early, you have to change them later. Think of the HVAC system. If you don't simulate it, you don't properly test your prototypes to know that these copper like pipes are pressing against each other and causing rupture, for instance. You learn it through the repair person that, oh, this is happening. So you have to go back, change your design, maybe change your manufacturing process, maybe get a different supplier, right? So that may be much more costly than figuring it out upfront that if you install, I don't know, the pipes so close to each other, they may be a cause of rupture. They may be like friction or whatever. So thinking about these aspects early on in the life cycle of the equipment or the product will be much more difficult to see the problem, but it will be much more easier to fix it or much less costly. And that's what design for reliability is. And briefly talking about maintainability. So reliability means you want something to last for a long time, right? Probabilistically speaking. Maintainability is you want something to be repairable in a probabilistic manner in a given amount of time. And if you have high reliability, short amount of repair, then you have a high availability overall. So I have a quick video to refresh all of you about maintenance and maintainability. And obviously this is not the focus of our class, maintenance and maintainability, but I just couldn't pass not showing you this video. And some of you may have seen it, but I think you'll enjoy it. So, who watches John Oliver? Okay, all right. Yeah, he's fun. 30 minutes, 17. All right, here's the importance of maintenance. barriers to any change, right? So, and reliability, setting up reliability shop in a plant that's been operating forever may be very difficult. And sometimes, at least from what I'm hearing from a lot of our guest speakers, is that you may be hired as a sole reliability engineer. So you have to start making all of these changes in the plant, changing the mindset. And you may face a lot of resistance in introducing all of these changes. There may be inadequate training for the personnel. There may be lack of management support. So there are some barriers that you may need to push through. And there are external barriers as well. So for instance, if you're designing something, you may be thinking about, should I do another test? Should I do another round of inspection, or like a round of improving the reliability, or should I just go with the production and hope that everything is going to work out? So there are barriers, but what is important is for you to make the right decisions. And I want to show you a video. And sometimes these right decisions cross with ethical considerations. So you have to be able to stand by your design, stand by the choices you make. You're all too young to remember this. I don't think I remember it, but I got the video. So this is not the right video. Oops. Okay. If I click on both. Okay, as you all saw, the shuttle blew up midair. So now here is after the effect. Right. So again, you not only have responsibilities towards your customers, you have responsibilities towards your plan, you have the ethical responsibilities and professional responsibilities. So be careful what you sign on or you don't, right? Because he said, and I love that sentence, that was the best decision I've made in my entire career, not to sign that form. So these are ethical responsibilities as engineers that we carry. All right. So speaking of reliability again, and design for reliability, we talked about the fact that if reliability comes late in the product lifecycle, it may be too expensive to change things. But then obviously it's easier to see things then. But then if you want to design for reliability, then it will be much more difficult to see the problems, but then much cheaper to change the design at that point. So we kind of want to engage with different aspects of reliability from early on in the product lifecycle. So it starts from like product lifecycle, starts with research, then goes to design, then prototyping, production, and goes to the customer. Traditional approach says that, okay, you have different considerations, let's say cost, time, quality, or reliability, and you typically pick two, and you typically pick the first two and go with cost and time, and don't worry about reliability. But then we talked about the fact that reliability is very important and how doing it late or delaying it can cause safety problems, ethical problems, liabilities, customer losing market share, and a lot of and competition and so on. So we want to go from traditional approach to design for reliability, which says that engage with reliability planning from the research from when you start researching your product. So it's essentially a roadmap that consists of multiple steps. And it has a lot of benefits in terms of optimizing warranty, increasing customer satisfaction, minimizing replacement costs, competitive edge, and so on. So it comes in a 6-step process. And this process doesn't necessarily go linearly. So you may cycle through some steps. And it is a never improving, a never stopping cycle. So you start from defining, identifying, analyzing, and assessing, quantify and improve, validate, and then monitor and control, and go back to define. And or sometimes you cycle through some of the other steps. So let's go through the 6 steps and see what they are. First, you start by defining reliability requirements. What it is that you want from the product, what it is that your customer wants, and then try to translate these reliability requirements into product requirements. A lot of it involves understanding the environment your product needs to operate in, understanding what your customer needs, understanding the competition, what the market wants. After defining reliability requirements, you want to identify what are the risks engaged. So is what you are producing a new product, or is it an old product? Is it new to your company, or is it is there a product like this out there at all, or is it an innovative product that may come with a lot of risk or unknown? And if you're changing part of the design, what part are you changing? What part may be introducing new risks? How changing one part of this component or this equipment will change how it interacts with other components or other pieces of equipment? How it would change upstream or downstream in your process when you're building it. So you want to focus on the different aspects of change and different aspects of how things can go wrong with your product. After that, you want to have a rough estimate of the reliability of your product, what you are designing. Finally, when you have a prototype, you want to start testing it. You want to do a lot of different techniques, some of which we are going to cover in this class, including live data analysis. You want to get a lot of samples, failure samples, to be able to see if you can describe or characterize probabilistically or statistically how this product is going to fail when it reaches the hand of the customer. And you want to go through a process where you test and you improve, and test and improve. By the end of the previous step, you're almost ready with a prototype. You're done with your prototype. You reach an acceptable design. Now you're not done yet, because it's one thing to get a product or a piece of equipment that's ready, that has a design that you like, that's acceptable to you in terms of reliability requirements. But then entering it into the manufacturing process introduces a lot of different difficulties. So you want to make sure the assembly goes right. You want to make sure that the human operators don't introduce any kind of problem when they are assembling it. You want to make sure that your supplies are right. You want to make sure that there is not a lot of vibration in the manufacturing process. It can scale, right? And you can produce a lot of that component or that product. And finally, and once you enter the manufacturing process, you want to continuously monitor and control the process. And this is the step where reliability engineers need to communicate with production engineers. And essentially the role almost changes to become the role of a quality engineer. And you have a toolbox to make it that you're going to use in all of the steps of design for reliability. I have posted a 6-page PDF on design for reliability that is an assignment. I want you to go through it and read it. It will discuss all of the steps that I just skimmed over in detail and introduce a lot of keywords, a lot of techniques that we're going to learn in this class, or you're going to hear from your guest speakers. So make sure you go through it. There's going to be questions from that document in I believe in your quiz, but possibly also in your homework assignment. All right. So now I want to hopefully wrap the class up with 2 examples to just finalize why we finally again further motivate why we care about reliability. And as reliability engineers, again, you have to convince your bosses that what you are proposing as reliability engineers matter, right? And that's through economics. If you want to communicate with the upper management, you have to put a number on it. Why they should care, why they should invest in increasing the size of your team, why they should invest in getting more maybe equipment for inspection, why they should invest on the design for reliability. Okay, so we're gonna for as the more money you spend on your reliability program, the more costly it gets. But then if you don't spend that money upfront, you incur costs as well. So there is an optimal place for or optimal point for how much you should spend to get the best bang for your buck. And this is what we want to see through 2 examples, 2 quick examples. So here's the first example. You will have you're producing new TV, and you have a reliability function. This is a reliability function for your TV, for how long it's gonna last. We typically show reliability functions with capital R, RT for reliability or survival. And anybody knows this function? Exponential, exactly. So it follows exponential process. Don't worry, we're going to cover that again. And you want to issue, the company issues a 1-year warranty for this product. So this function gives the probability that the component or this TV is going to last up to time t, and you want to have a 1-year warranty on the product. So assuming that customers use their TV 3 hours a day, 365 days a year. So total, you want your TV to last. This gives the probability that the TV lasts for a year, which is about 90%. So 90% of TVs last for a year. Okay, given that piece of information, would you and we know that each TV replacement costs about $600, and the company sells 50,000 TVs per year. So, okay, given this information, is it worth spending $1 million on which is a lot of money, right? $1 million on improving the reliability in year 1 from 90.9 to 0.95? Yes, no? Can you do it in your head, or do you need a piece of paper? Okay. All right, 2 quick examples. You need to write back of an envelope, like you need to write something very quickly, do the calculations, or do the calculation in your computer or in your head. But I want to know what you guys think. $1 million is a lot of money. You want to convince your boss that it is worth it. You have to show him or her why. Show me why. If you're going to invest, or why you're not going to invest. And feel free to talk to each other. All right. Anybody has an answer? Do you invest? Who invests? $1 million is a lot of money, but you invest in reliability. There you go, right? The first time you convince somebody that reliability is worth it. Can you do the math for me? Like again, very quickly. So can somebody speak up why they choose to invest? It saves $500,000. Okay, let's walk through it. So if you don't do it, right, reliability is 0.9. Okay, so the difference, this plus $1 million, this would be 2.5. So actually, by spending in your reliability program, you're earning $500,000, even though you invested that much. You have a question? All right, perfect. So let's look at the last example of the class. I want to introduce it through this example. I want to introduce a concept which you may see in your homework. Mean time to failure, mean time between failure. Mean time to failure means the average time that it takes for a component to fail. Mean time between failure, it means the average time for that it takes for a component to fail. What do you think the difference is between mean time to failure and mean time between failure? Exactly. So mean time to failure, you typically speak about mean time to failure for a new product. So it's a mean time to failure for this new product, or mean time to failure to the first failure. Mean time between failure kind of has this embedded assumption that after that failure, you maintain it, you bring it up, you let it work, again it fails, you maintain it, you bring it up. So mean time between failure has this kind of implication that you maintain your components somehow, right? So, but again, they're very similar, you calculate them the same way. So it's very similar. Okay, so for instance, if I have mean time between failures to be like 6 hours, and let's say repair happens instantaneously, so on average every 6 hours I have a failure, right? So that will be the rate of failure, 1/6, right? Rate and mean, they go they have a reverse relationship. Okay, so now let's look at this example. Suppose cost of repairing a unit that fails is $100. Okay, and we need to maintain production for 2,000 hours. How much can we save if we improve mean time between failure from 6 hours to 8 hours? Again, very quick, straightforward calculation. How much do we save? What do you guys get? What? 8,400? Okay, yeah, that's what I got. Right. So can somebody walk me through it? Hmm. Perfect. Okay, so this is number one, C1, C2. You find delta C, which is this much. Right? All right, so this is it. This is how you tie reliability to cost, right? We are not going to talk about the economics of reliability in this class. I just wanted to show you in the two very quick examples how after you are improving reliability, figuring out when things are going to fail or like characterizing failures in a plant in like wherever you work, right? How you should introduce those concepts to a higher manager who is writing a check. So this is just to tie things up. Again, as reliability engineers, you're going to be with the details, how to estimate the mean time to failure, how to figure out whether 90% fail or 95% fail within so many hours, and how you may be able to change things to make sure that maybe like through redundancy, through like putting them in as part of the system, you can increase the reliability. You can do things with reliability. But this is at the end of the day, these calculations of to change to incorporate the economics is something that you may need to do when you're presenting all of your results to put it in context for whoever essentially is gonna be your boss. All right, with that, we conclude this first class. We're gonna have homework. We're gonna have quiz. Don't forget about them. Tuesday. Yes. Have a good weekend, guys.